Hello everyone, in this video I'm going to continue with the third question in chapter 2, volt-ampere characteristics of transistor. There are mainly the following three aspects: input characteristic curve, line input characteristic curve, and limit parameters of transistor. The so-called volt-ampere characteristics of the transistor refers to the relationship between the current and voltage of the transistor. Then we can draw the relation curve of the transistor current and voltage by the experimental method. We call this the volt-ampere characteristic curve. For the child, it is most widely used when the common emitter is connected. Its input characteristic curve and output characteristic curve. So let's take the common emitter connection as an example to introduce the voltage ampere characteristics of the child. In the top right corner, the child is a three-terminal device, but as a four-terminal network. The emitter then serves as a common reference point for input and output, base as input and collector as output. The parameter VBE is the input voltage, IB is the input current, and VCE is the input voltage. IC is the current at the input. So we are going to analyze the relationship between IB and VBE, and we are going to plot the relationship between IB and VBE. The premise is the output voltage VCE as a variable. When VCE takes a certain constant value, we can draw an input characteristic curve. When VCE changes to different values, we can draw a number of relationship curves between IB and VBE, which are called input characteristic curves. On the output side, we need to plot the relationship between IC and VCE, or draw a curve. So the premise is that the current at the input is IB. When I take a constant value of IB, I can draw an output characteristic curve. When IB is different, we can draw multiple output characteristic curves. We call this set of curves the output characteristic curve family. Okay, so let's talk about what are the characteristics of the input characteristic curve and the output characteristic curve. Let's start with the input characteristic curve. The horizontal axis is VBE. The vertical axis is IB. So when the reference VCE is equal to 0 volts, we can draw an input characteristic curve like this. And you can see that it's very similar to the volt-ampere behavior of a diode. When VBE is greater than the diode zone voltage, IB increases exponentially with VBE. When VBE is less than 0, the reverse saturation current is very small, when the absolute value of VBE is greater than the absolute value of VBR BEO. The emitter junction is in a state of breakdown. As VCE increases, we plot the input characteristic curve when VCE is equal to 0.3 volts. As you can see from this picture, when VCE is less than 0.3 volts, if the x-coordinate of VBE remains unchanged, IB is the y-coordinate which will decrease rapidly with the increase of VCE, indicating that it is in the saturation region. As VCE increases, IB decreases rapidly, and VCE increases. So increasing the collector's ability to collect free electrons, the ability of the base region to contain free electrons is reduced. So IB is rapidly reduced, which is one of the characteristics of it working in the saturated region. And as VCE continues to grow, we can plot this input characteristic curve. When VCE is equal to 10 volts, which is the rightmost curve. As we can see, the transistor works in the large discharge area. At this point, IB can be considered almost unchanged by VCE. In engineering, we usually think of the transistor in the discharge area. The IB is almost unchanged, but as you can see from this diagram, as VCE increases, IB also decreases slightly, and this is called the early effect. So let's do a quick explanation of what is the early effect. The early effect is when the transistor is in the amplification zone as VCE increases, as the reverse bias voltage of the collector increases gradually. The width of the collector increases, and the width of the base area decreases. For example, when WB0 to WB, the ability or opportunity for the holes in the base region to compound free electrons is slightly reduced, resulting in a slightly reduced base current IB. This is known as the early effect or base width modulation effect. We can plot multiple input characteristic curves. IB is equal to 0 μA, 10 μA, all the way to 40 μA. We draw a bunch of output characteristic curves. As the applied voltage changes, or as the VCE changes, we can divide the input characteristic into 4 regions: saturation zone, amplifier zone, breakdown zone, and cutoff zone. Firstly, we look at the amplifier zone. When the transistor is operating in the amplifier zone, its emission junction is positively biased, and the collector junction is negatively biased. At this time, we can observe that these curves are almost parallel. That is, IC is almost unchanged with the change of VCE. The expression for IC is equal to beta times IB plus ICEO. If you ignore ICEO, you can see the IC is almost exclusively controlled by IB, and it is linearly proportional to IB, which we call the current amplification zone. This is a characteristic of the amplification zone. But we can see that from this diagram, the output characteristic curve is slightly skewed. With increase of VCE, it is slightly upward. This is what we call the early effect. If you want to think about the early effect in practice, how should the actual expression for IC be modified? So let's talk about that. If you don't take into account the early effect, IC and VBE are exponential rates. Now let's draw a set of output characteristic curves. The variable changed from IB to VBE. We can get a set of curves that look like this. These output characteristic curves are extended in the opposite direction of the horizontal axis, so that the reverse extension lines converge to a point, which we call point A. The x-coordinate of A is called VA. We need to discuss with the increment of VCE. What is the incremental delta IC of IC? Because these two triangles are similar triangles. So you can get the following relational expression. Delta IC, then VCE, is equal to the absolute value of the IC by VA. In that case, delta IC is equal to VCE multiplied by the IC. Go up, then the absolute value of the VA. Once we get this increment, then we can derive the expression for IC compensation. IC is equal to delta IC plus the index expression. So you get IC is equal to IS times E to VBE over VT times 1 minus the absolute value of VA over VCE. This is our actual situation when you need to think about the early effect, the actual expression for IC. Now let's look at the cutoff region. In engineering, it is generally thought that when IB is equal to 0 μA, that is the bottom dotted line. When IB is equal to 0 μA, the transistor is considered to be in the cutoff zone. So the region below the curve of 0 μA is the cutoff zone of the transistor. IC is equal to ICEO. This is the cutoff zone of the transistor. Now let's look at the saturation zone. When the transistor is in the saturation zone, its emission junction and collector junction are positively biased. In the input characteristic curve, we see a dotted line here, and the approximate abscissa of the dotted line is 0.3 volts. VCE is approximately 0.3 volts. The region to the left of the curve is the saturation region. In the saturation region, as VCE increases, IC increases rapidly. The fact is that as the VCE grows, the collector's ability to collect free electrons or to collect multiple electrons from the emission region gradually increases. Then the IC will increase. but the value of IC in the saturation region is less than beta IB, because in the amplification area, IC is equal to beta IB. So in the saturation zone, its current is less than this value. This is the input characteristic curve. We can see that its saturation region is such a characteristic. Now let's look at the breakdown zone. With the increase of VCE, the reverse bias voltage on the transistor junction will also increase. When the reverse voltage increases to its breakdown voltage, then the transistor will enter the breakdown zone. So the area to the right of this dotted line is the breakdown area. Here, the transistor has two characteristic parameters. When IB is equal to 0 μA and is equal to 0, with the increase of VCE, the voltage value corresponding to VCE at the breakdown of the transistor junction is called VBR CEO. This is one of its voltage parameters. The other voltage parameter is when IC is equal to 0. With the increase of VCE, when the collector junction breaks down, the corresponding breakdown voltage VCE is equal to VBR CBO. This is its other breakdown voltage. When these two breakdown voltages are compared, usually VBR CEO is less than VBR CBO. Let's discuss the limit parameters of the transistor. We can see that there is an ICM at the top of the graph. It represents the maximum operating current of the transistor. If the working current of the transistor is beyond this range of ICM, then it enters the overcurrent region. Let's look at the triode, and the maximum operating voltage is VBR CEO. If the working voltage of the transistor exceeds this voltage, it enters the overvoltage zone. The right curve is the largest transistor, power loss area, maximum power loss line. If the working area of the transistor exceeds this right line into the right area, it was into the damage area. Then the safe working area of the transistor is by PCM. ICM and VBR CEO to define. When the transistor is working properly, it usually works in a safe area. Okay, so that's the end of this section. Thank you.